Hi everyone. So in this exciting installment of the hardware-software interface, we're going to expand our knowledge of embedded systems. And particularly so far, we've really just looked at what an embedded system is. We've tried to define some of the basics of just what does it mean to be an embedded system. A core part of embedded systems is what is often referred to as embedded control. Embedded control is the software logic that decides, hey, what should happen, right? Based on what sensor information comes in, what information should come out to deal with actuation of our system. Okay. Now, there's a different way of thinking when it comes to dealing with embedded control software. And this is because when we're dealing with embedded control software, we're almost always in a situation where we have this time-oriented behavior. Now, what am I referring to when I talk about time-oriented behavior? Well, I'm talking about where we have a system where the functionality, right, where the outputs depend on the order in which the input events occurred. Now, that definition probably seems a little murky. It makes a lot more sense when you just start to think of some examples. And when you look at examples, you can start to see why this is super common when we're talking about an embedded system. Okay, so like for one, imagine you have a simple electronic lock, right? The user has to press and release buttons, and they got to do it in a certain order, right? Maybe button A1, then A0, then A2, done in that order, and it'll unlock the door. Okay, so clearly the sequence of events is very important. If you did something different with that lock, the lock's not going to open, right? That is what we mean by time-oriented behavior, right? What the system does depends on the order in which the inputs arrive, okay? Another example might be a toll booth, right? You imagine a toll booth operator, right, operating a toll gate, okay? The toll booth operator might press button A0, right? And then keep the gate up as long as it's detecting that a car is near the gate based on sensor A1, right? So that the gate, right, presses a button, the gate goes up, right? And as long as that car is still there, it hasn't passed through that location, it's going to go ahead and keep that gate open, right? So you have this order of events that takes place, right? Where the gate doesn't lift until the operator presses the button, and the gate doesn't lower until the sensor input is of a certain value. Time-oriented, right? The functionality of the system depends on the order of how the inputs arrive. Okay. Now let's look at a really simple example that explains time-oriented behavior. And one thing I want to point out right at the beginning, okay, is because this could be confusing, so I want to be really clear on this, is that C, in the form that we've seen it so far, is really bad at handling time-oriented behavior. Okay. Now we're going to look at how we look at a different paradigm, okay, involving state machines to make this process much simpler. So we can still do it in C, but we're going to code things a different way. So I'm going to show you an example, right? This code that we're looking at here is basically a bad way of doing this, okay? And I'm always very hesitant to share bad ways of building something because I don't want to have people misinterpret what I'm showing as a way of saying, hey, this is the proper way to do it, okay? So keep it in mind, this is a bad example. However, I think it's important and necessary that we look at this example, right? Because we need to look at why this example kind of falls apart before we can look at how to do it correctly. Okay, otherwise it's hard to understand why we're doing some other things. So we have to look at what some of the flaws are. Okay, enough of that. Let me kind of make this concrete. So let's imagine we've got a carousel and it's going around and around and around. Okay, and we have a sensor here, and our sensor is going to determine, is basically going to count how many times the carousel rotates. Okay, so we've got this sensor A1, A0, okay, and every time a certain location represented with that red dot, every time that passes by the sensor, okay, the sensor's A0 is going to go from 0 to 1. Okay? And what we want to do is we want to just keep a counter. Okay? Every time that it rotates, we want to bump B up by 1. Okay? So let's take a moment, and I think I'm going to get a little bit of extra room to write this. Let's take a moment to think about what does this look like in terms of a waveform diagram. Okay, so let's just kind of recap here. We have our input. Okay, we have our input A0, and what's going to happen, right, is we have A0, and A0, right, is most of the time is going to stay flat. Okay, let's make sure this is all, there we go. Most of the time it's going to stay flat, and then every once in a while it completes the loop, and it's going to stay up for a little bit, right? So we're imagining this is all digital, right, 0 or 1, right? So this is our input signal. It's the carousel's rotating, and oh, you know, it completed a loop, right? So we see a waveform that looks something like this. Okay, now what we want to do, and what we really care about, is at this rising edge here. Okay, at the rising edge, this is where we want to increment our counter. Okay, so we're really concerned is we really want to increment our counter at this rising edge. Okay, that's the trigger. That's the trigger in which we want to have something occur, is at that rising edge. Now, let's make sure that that's really clear, right? Because what we don't want to have happen, this is where it's important to keep in mind when things should occur. What we don't want to have happen is that B continuously gets updated, right, while this value is high. So if we imagine we're sampling, right? We don't want to have B get updated multiple times, right? If we're sampling, you know, repeatedly up here at when A is 1, we don't want B to get counted 3 times or more when it passes through and rotates just once. So it should only happen at the rising edge. Okay? Only happen at the rising edge. That's an important thing to note. Okay? Now let's look at how this code here does that. Okay? How does it do that? Well, first we got some initial configuration. So this is fairly basic. Right? We have some initial configuration happening. This is like kind of our startup code. Okay? Everything before this while loop. Then this while loop here, okay, this is our infinite loop. Okay, that's our infinite loop. Notice while 1 stands for true, right? Always true. It's never going to leave. Okay. Now, if you think back to doing like Arduino programming or anything like that, you have that loop function that's effectively the same thing. So just to kind of point that out. Okay. Now, let's take a look at what this while loop does. And first of all, the syntax is a little weird. I want to point out that when you have the semicolon there, that's equivalent to having a while loop that does nothing in the body. Okay, like open bracket, closing bracket. Okay, it's equivalent to that. And what that's doing is it's saying basically wait. Okay, continue to wait. It's just going to loop and loop and loop and loop, okay? And it says wait while not A0, okay? So while not A0. So what that means, right, is if we think about this, well, if A0 was 1, okay, right, then not 1 would be 0, which would be false, okay? So what this is doing, right? Think about what, if we look at just this condition here, right? We take a look at this condition down here and say, well, when is it going to stay on that line, right? When is the code going to stay on that line? Or better yet, when is it going to leave that line? When is it going to leave that while loop? Okay? And it will leave that while loop, okay, as soon as A0 is 1. Okay? It effectively leaves the while loop, right, at this rising edge. Okay? It leaves at the rising edge when A0 goes from an input of 0 to 1. Okay? The moment, right, the moment this, not A0, right, the moment A0 becomes 1, then not 1, right, or not true is false. Okay? And we leave that loop. We then increment B. Okay? So this is wait. The first one that I pointed to is wait for the rising edge. Okay? And this bottom one is a wait for the falling edge. Okay? Effectively, we want to make sure that we don't go back around and wait for we can't really wait for the rising edge. Okay, we can't wait for the rising edge until we've actually fallen back and A0 is equal to 0. Okay. Now, I want to point out a couple things here. If you found that code confusing, right, that's rightly so. Imagine if we started, this is a very simple, like if we had an embedded system where we had, our microcontroller was connected to the sensor, right, and it was just keeping track of how many loops there were, how many rotations of the carousel, right? That's a pretty simple functionality, just counting number of basically ticks of that sensor, okay? And the code gets pretty nasty pretty quick. So if you imagine you built something more sophisticated, this paradigm here, which is similar to what we've seen in other C examples, is nasty, right? It's not ideal. So what we want to move towards is a better approach, okay? But before we do that, let me give you another example to kind of illustrate why and how quickly it gets so nasty, right? I think it'll just make it sink in, and then we can move towards a better approach, okay? Which I might wait till the next video to do so that we keep the video short. Okay. Here we have what we're trying to do, okay, is we've got some code that's a little bit more in depth. And what this code is doing is, let's imagine this previous example where B can only increase, it can only increment. Let's imagine we added an additional button, okay, an additional button that allowed us to reset B, okay. So let's imagine we've got our carousel, okay, we have B, okay, we want to initialize it to 0, okay, we have our sensor A0 that is determining when that carousel loops, okay, and then we're also going to have a button here connected to A1 that is going to reset our counter, which we're calling B. Okay. So it's pretty much the same thing as before, except we have this additional reset thing going on here. Okay. All right. So this code for doing it, let's look at how it works, and let me just make a little so that we can go ahead and draw this out. Okay, so let's look at this and let's draw what's happening, okay? So as we can see, this logic here, okay, we have this little bit more complicated logic of what we're waiting for, okay? What we're effectively waiting for, right, is the situation where we have a rising edge of either A0 or A1. So let's look at, we can look at our waveform diagram, and we have A0 is our kind of rotation, right? We've got where it kind of rotates. Okay, so maybe it's sped up and the rotation's a little faster, right, based on that diagram. And then we have A1, which would be like, okay, maybe it ticked and incremented B a couple times, and then somebody pressed the button. Okay. So this is resetting it after 2 rotations. What we want to have happen is we need to trigger something happening either at this rising edge or this rising edge. Okay, so what this is doing, this while loop, it says, right, wait for either A0 or A1 rising edge. Okay, now notice when I wrote it in English like that, I used or. When it's written in the code, it's and, right? Because it's effectively kind of saying the opposite. Like I'm saying wait for that to happen, right? The while loop kind of has the inverse of that. It's saying, hey, continue to wait while they're both 0. Okay? So you kind of understand how that works. Like when I say it, I think the more intuitive way to phrase it in English is say, hey, wait for the rising edge of either input, right? But in terms of writing it in code, it's kind of, we're saying, hey, continue to wait while they're both 0. Okay? Really saying the same thing, right? One, you're talking about under what condition are you waiting. The other is talking about which condition you're no longer waiting. So they're just the inverse. Okay. If we do that, then in here, we have our logic of what to do, right? If it was the rising edge of A1, we reset B. Okay, so if it was the rising edge of A1, we're going to reset B. If it was the rising edge of A0, we're going to go ahead and increment B, and then we're going to wait. Okay, we're going to continue to wait until we have the falling edge here. Okay, wait for the falling edge. Okay, of A0. Okay. Now, we don't really need to wait for the falling edge for A1, because if we kept on running through, excuse me, if we kept on running through and hitting this reset over and over again, it doesn't really matter. You might actually want that while the button's being held, right? Just continuing to reset the thing, which is fine. You just keep setting it back to 0 while someone's holding the button. Okay, what's the point of this? Mostly showing how this gets complicated. Okay, this gets complicated pretty fast. Writing it in C code this way, where you have all these while loops, right? You have these while loops with nothing in the body. What we want to move towards is using state machines, okay, state machines in such a way, right, to be able to simplify the control logic. Okay. Now I'm going to save that for the next video, though. I'd like to keep this short, right? So just to summarize, keep in mind that this video is illustrating a scenario, okay, scenario where C fails to capture, okay, the time-oriented behavior correctly, okay? Well, not correctly, but it makes it difficult, right? We want to make writing code simple. We want to approach writing code in such a way in which it's simple and intuitive to design and execute. And unfortunately, in this case, right, doing it this way, it's not that simple. It gets pretty complicated pretty quick. So we want to move towards a more simplified model. And that's what we're going to be heading towards. Okay? And we'll talk about that in the next video. So please stay healthy, stay safe, and I will talk to you in the next video or in person.